The third exception to the octet rule applies to elements that have an expanded octet. This rule specifically applies to elements that are in the third period or beyond, and it is allowable because of the orbitals that they have. If you look at the elements in the third period and beyond, say for example sulfur. When you look at sulfur, we know that its highest energy electron sits in a 3p orbital. What we also know is that because that electron sits in the third shell, we know that the sulfur also has a set of 3d orbitals as well. So that when we talk about elements that are going to be expanding their octets, these elements are going to be able to use unoccupied higher energy d orbitals from their valence shell in order to accommodate the extra electron density. So there are a couple of key things to make sure you are aware of. First of all, it's the elements that are in the third period and beyond that are capable of holding more than 8 electrons because of those empty d orbitals. We'll commonly see sulfur, phosphorus, bromine, and iodine. And it's also very important to remember that the reason these elements can do this has to do with the number of orbitals they have. Elements in the first and second period, like hydrogen, oxygen, carbon, these elements can never have an expanded octet, and the reason is that they simply don't have the orbitals. Hydrogen, when it bonds with its orbitals from the first shell, it's only a 1s orbital. It can only ever have one bond. When the elements from the second period bond, they're bonding with those second shell orbitals, which includes s and p orbitals, allowing them to go up to an octet. The first two examples involving expanded octets are sulfur hexafluoride and xenon difluoride. These examples follow all of the rules for Lewis structures as we have already laid them out. What I want you to do is pause the video and draw the structure of these molecules. Follow the rules for Lewis structures as we've already discussed them, and draw these two structures by following all of those rules. Calculate all of your formal charges as well. So I'm going to jump back into the process here at step 3. I've already calculated my total number of electrons to be 48. I've chosen my central atom, and I've bonded all of my other atoms to the central atom. In doing so, that means I placed all 6 fluorines around the sulfur, and I used 12 electrons to do that. I have 36 electrons left, and if I follow my rules, rule number 3 tells me to complete the octets for my outer atoms. So I'm going to give this fluorine 6 electrons to complete its octet, and I'm going to do the same for my other fluorines. So now that I've given 6 fluorines each 6 electrons, I've used all 36 of my remaining electrons, and I'm out of electrons. So this is the structure that my rules brought me to. When I look at all of the atoms in this structure, I will see that each of my fluorines that has 1 bond and 3 lone pairs carries a formal charge of 0. If I calculate the formal charge on the sulfur, sulfur comes to this structure with 6 valence electrons. In this structure, it sees 0 electrons in lone pairs, and in this structure, it sees 12 electrons in bonds. So 6 minus 0 minus half of 12 gives me a formal charge of 0. So that when we understand why sulfur hexafluoride is a molecule that exists, it has to do with the fact that the sulfur, even though it's expanded its octet, it has expanded that octet and maintained a formal charge of 0. So that means that the sulfur is happy with the electron density that it sees. If I look at the next structure of xenon difluoride, I've calculated my number of electrons for the structure and I get 22. Xenon is in group 8A. It's a noble gas. It doesn't participate in a lot of chemistry, but it will react with fluorine. It will bring 8 valence electrons to this structure. Each of my fluorines will bring 7 valence electrons to the structure, giving me a total of 22. So that I've chosen xenon to be my central atom, I've bonded my 2 fluorines to it, and in doing so, I used 4 electrons. That means that I have 18 electrons left for the structure. So that if I follow my rules, rule number 3 tells me to complete the octets for the outer atoms. So I'm going to give this fluorine 6 electrons. I'm going to give this fluorine 6 electrons. And in doing so, I use 12 electrons. I have 6 left. Rule number 4 tells me to put any remaining electrons on my central atom. So I will do that. I have 6 electrons, so I'm going to add those electrons in the form of 3 lone pairs. That now uses all 22 of my electrons. I'm out of electrons. And when I look at this structure and I calculate formal charges, my fluorine has a formal charge of 0. When I calculate the formal charge on the xenon, it comes to the structure with 8 valence electrons. In the structure, it sees 6 electrons in lone pairs. In the structure, it sees 4 electrons in bonds, so that 8 minus 6 minus half of 4 gives me a formal charge on the xenon of 0. So the xenon has undergone chemistry, the xenon has reacted with fluorine, but in doing so it has maintained an appropriate amount of electron density for it, and it has maintained that formal charge of 0. Xenon is in the 5th period of the periodic table, so that means that xenon is forming all of the bonds that we see here using its 5s, 5p, and 5d orbitals. So when it comes to elements that have an expanded octet, there's a more complex question that we can look at with expanded octets, and that is similar to what you see here. So for the following question, it says, for the following molecules, draw the best Lewis structure when considering formal charge and expanded octet, if appropriate. So there's different directions that apply to questions like this second case compared to what we saw before with sulfur hexafluoride and xenon difluoride. In this case, the directions are going to be a little more specific to make you think a little harder about the questions that we're looking at. For sulfur hexafluoride and xenon difluoride, the directions simply tell you to draw the Lewis structure. These structures, again, require a little bit more thought. So in looking at the sulfate ion, what I want you to do is I want you to pause the video and I want you to draw the structure that follows the rules for Lewis structures as we've laid them out so far in class. So if you've followed all of the rules as we've laid them out in class so far, this is the structure that you should get. When you go in and calculate the formal charges on these structures, you will find that all of your oxygens carry a formal charge of -1. That means that if we know that the sum of the formal charges must be equal to the overall charge on the molecule, and we've got a -1, -1, -1, -1, the sum must be -2, we should already know what the formal charge on the sulfur is going to be. When we do the calculation on the sulfur, we find that the formal charge is +2. So this is a structure that has a lot of formal charge. All 4 of my oxygens see too much electron density. My sulfur sees not quite enough electron density. And in this structure, because we have so much formal charge, and because our central atom has a positive formal charge, our outer atoms have lots of lone pairs, we want to look to see if there's anything we can do to make this structure better. And let's use the following series of structures to help us get to the best Lewis structure for the sulfate ion. So this is the structure that we were just looking at, where all of our oxygens had a formal charge of -1 and our sulfur had a formal charge of +2. When we're looking at structures where we're asked to consider expanded octets, if appropriate, we're looking to see if expanding the octet of an atom will help us get to a better structure. And remember that whenever we're talking about better structures, we're almost always talking about formal charge considerations. What we're going to do here is we're going to look at our outer atoms. I'm going to look at this oxygen right here. This oxygen has lone pairs. It has a formal charge of -1. My sulfur has a formal charge of +2. So one of the things that can happen is that this oxygen can donate that electron pair towards the sulfur, and that's going to get me to this structure here, where this oxygen now has a double bond between itself and the sulfur. My other 3 oxygens still have a single bond and 3 lone pairs. The question is this structure any better than the original structure that we drew? And in order to answer that, we're going to look at our formal charges. Go ahead and calculate all of the formal charges for the structure. So that as we look at all of the formal charges, we now see some differences. Here I have 3 oxygens with a formal charge of -1, whereas over here I had 4 oxygens with a formal charge of -1. Here my sulfur has a formal charge of +1, here it had a formal charge of +2. Here I have 1 oxygen that I'm able to get to a formal charge of 0, and that was not the case here. So overall, in this second structure, the formal charges that I have are better than what I had in the first structure. So the question is, am I done? Is this the best resonance structure that I can draw for the sulfate ion, or can I keep going? And the best way for you to answer that question is to keep going. If one double bond made the structure better, what happens if we add another double bond? So to answer that, what we're going to do is we're going to take this lone pair and we're going to share this lone pair with the sulfur. So we're going to share this lone pair with the sulfur, and that's going to give us this structure here. And so in this structure, is this structure any better than what we had before? To answer that question, we need to calculate all of the formal charges. The formal charges on my oxygens with 2 bonds and 2 lone pair will be 0. The formal charges on my oxygens that have 1 bond and 3 lone pairs will be -1. So already, if I know that the sum of my formal charges is equal to the overall charge of the ion, which is -2, these two are 0, these two are -1, I should already know what the formal charge on the sulfur is going to be. When I do the calculation for the formal charge on the sulfur, what I find is that the sulfur's formal charge is now 0. So that in this structure, we have formal charge, but we have the minimum amount of formal charge. I have 2 oxygen atoms that are carrying a formal charge of -1, and that's really the minimum formal charge we're going to have because that ion has a charge of -2. I have 2 oxygens with a formal charge of 0, that's good. I have my sulfur now with a formal charge of 0, that's also good. So just like we did before, I want to make sure you understand. We made 1 double bond and got a better structure. We made 2 double bonds and got a better structure still. What happens if we make a 3rd double bond? To answer that question, what we're going to do is we're going to take this lone pair and we're going to share that lone pair now with the sulfur, and we're going to look at the structure that results. Go ahead and calculate all of your formal charges and see if you think this structure is better than what we just drew. So that when you calculate all of the formal charges in this structure, you see that we have 3 oxygens that carry a formal charge of 0, 1 oxygen that carries a formal charge of -1, and my sulfur now carries a formal charge of -1 as well. The sum of my formal charges is still -2, which is the charge of my ion, but if I look at the atoms that now bear this formal charge, I see that it's not as good as what I had in the previous structure. Because in this structure, my sulfur is less electronegative than my oxygens, yet my sulfur is now the atom that bears a formal charge of -1. So getting an additional oxygen to 0 at the cost of bringing the sulfur to a formal charge of -1 is not going to be favorable. Oxygen is more electronegative. It will maintain that formal charge of -1 over the sulfur taking on that formal charge of -1. So that this structure here is not better than the previous structure that we drew. And it's going to be this structure here that is our best structure. This structure here that's going to be our best Lewis structure for the sulfate ion. Now for this structure, this is not the only structure like this that we could draw. This is one of 6 equivalent resonance structures that you can draw for the sulfate ion. There are a total of 6 equivalent resonance structures for the sulfate ion that we could draw. All 6 of those structures are shown here. There's different patterns that we can have for the 2 oxygen-sulfur double bonds and 2 oxygen-sulfur single bonds that we have across these 6 structures. This is the one we drew on the previous page, but any of these 6 structures would be accepted as a correct answer. In a question like this one, you would be told that you would only need to draw 1 equivalent resonance structure for the molecule. I could also ask you a question where I ask you to draw all 6 equivalent resonance structures for the sulfate ion. For the phosphate ion, we see something similar. You should be able to draw a best Lewis structure when considering formal charge and an expanded octet. For the phosphate ion, there are a total of 4 equivalent resonance structures that you should come up with. Go ahead and try the phosphate ion on your own, and I'll put the solution on Blackboard.